This question is from GATE 2017 Mechanical Engineering Paper Set 1, question number 46. A thin uniform rigid bar of length L and mass capital M is hinged at point O, located at a distance of capital L by 3 from one of its ends. The bar is further supported using spring, each of stiffness K, located at two ends. A particle of mass small m, which is capital M by 4, is fixed at one end of the bar as shown in the figure. For small rotations of the bar about O, the natural frequency of the system is dash. Let's find out. So to find out natural frequency, we use the definition. Natural frequency of the system is under root coefficient of the displacement, that is K star, the stiffness component, divided by coefficient of acceleration, that is M star, mass component. These are equivalent values. These are not the absolute stiffness or absolute mass value. We have a generalized coordinate theta here. As the bar rotates, we have the coordinate theta, which is the independent coordinate. Displacement of each of the points of this bar can be calculated in terms of theta, and that's why theta is called the independent coordinate. This is also theta. Now, in order to find out the equivalent stiffness and equivalent mass components, we'll have to formulate the equation of motion, which is nothing but m star theta double dot plus k star theta equal to 0. The damping force is 0 here and there is no external stimulation, and that is why we only have the inertia force component and the stiffness force component. Let's formulate the equation of motion in terms of Lagrange's equation of motion, that is time derivative of partial derivative of Lagrange with respect to theta dot, that is velocity, minus partial derivative of Lagrange with respect to displacement theta, which is equal to 0. Now this is the general form of Lagrange equation of motion, where Lagrange term is nothing but difference between potential and kinetic energy. T is the kinetic energy and V is the potential energy. Now we can see that there are springs and there are masses in the system. Kinetic energy will be possessed by the mass and potential energy will be possessed by the springs, because they store energy in terms of potential energy by the virtue of their configuration, while masses are undergoing motion and therefore their energy expense is in terms of kinetic energy. So let's find out T and V here. Kinetic energy T can be found out like this. So we have theta is our independent coordinate. So naturally kinetic energy will be in terms of moment of inertia rather than in terms of mass. So for the bar, we have the moment of inertia to be ml square by 9, and therefore its kinetic energy will be half into moment of inertia of the bar about the pivot point, that is point O, we'll write it as IO, into omega square, which is nothing but theta dot square, the velocity square. Plus we also have this small mass small m. For that we will write half into moment of inertia of the small mass, of course about point O, into velocity of the small mass is also theta dot square. So we can multiply this with theta dot square. Now our task is to find out the moment of inertia of the bar about point O and of the mass about point O. Let's do that. For IO, we'll have to use the parallel axis theorem because we know how to calculate the moment of inertia of a bar about its center. So moment of inertia of the bar about its own center plus mass of the bar m into distance between its center and pivot point O. So this distance is nothing but capital L by 2 is the half distance here minus this L by 3 will give us this remaining distance. So we have m into L by 2 minus L by 3 square of this, which is equal to IC is nothing but ml square by 12. This is a standard result which you need to remember for the exam, plus capital M into L by 2 minus L by 3 is nothing but 3L minus 2L by 6, which is L by 6 whole square. L by 6 whole square is L square by 36. After adding this, we get this as ml square by 9, because this becomes 3 plus 1 4 by 36, which is 1 by 9, ml square by 9. We have the value of IO. Now we need to find out I of mass m about point O. So let me write it here itself. We have I of the mass about point O is equal to small m, that is capital M by 4 into, what is the distance? It is L minus L by 3 whole square. L minus L by 3 is nothing but 2L by 3. So it is 2L by 3 whole square. This after simplifying we get 4 by 4 1. So ml square by 9. Same as this one. So we have half into ml square by 9 theta dot square plus half into ml square by 9 theta dot square, which is nothing but 1 by 9 plus 1 by 9 into the common terms. This turns out to be ml square theta dot square by 9. Now let's find out the potential energy V. For potential energy, spring is storing it. So we have half into K1 x1 square plus half into K2 x2 square. This is also the standard formula for potential energy of a spring, half into Kx square, where x1 and x2 are deformations of the springs having spring constants K1 and K2. Now we can find out x1 and x2 just by using the triangle relationships in the figure. So this much distance is given L by 3. This is x1, this is x2 if angle is theta. x1 will be simply L theta by 3 and x2 will be 2L by 3 into theta. So let's write down half into K can be taken common. x1 is L theta by 3 whole square plus x2 is 2L theta by 3 whole square. Let's simplify. We have V is equal to half into K into. This becomes L square theta square by 9 plus 4 L square theta square by 9. So it is 1 plus 4, 5 L square theta square by 9. This is equal to 5 by 18 K L square theta square. Let's write down the Lagrange's equation that we have seen in the first step. D by dt of dou L by dou theta dot. So in T minus V term, that is Lagrange term, we have theta dot only in the term of kinetic energy T. So derivative of this term will be taken here. We have ml square theta dot square by 9. Derivative of this term with respect to theta dot is nothing but 2 into ml square theta dot by 9 minus dou L by dou theta. So again, it is partial derivative of Lagrange term with respect to displacement. So when we take T minus V, we already have a negative sign here. And therefore the derivative is minus of 2 into 5, that is 10 by 18 KL square theta square is equal to 0. Again, writing in the final terms, we have derivative of this term with respect to time is 2ml square theta double dot by 9 plus 10 by 18 is nothing but 5 by 9 KL square theta square equal to 0. Now we have K star and M star. Let's put it in the formula for natural frequency. We have under root of 5 by 9 KL square upon 2 ml square by 9. We have the natural frequency to be 9 by 9 gives us 1. 5 by 2 K by capital M. This gives us the natural frequency. Let's go back and mark the correct option. Answer is in option B. Natural frequency of the system is under root 5K by 2M. To learn more about generalized single degree of freedom systems, you can refer to the NPTEL video, Module 1, Lecture 17, Generalized Single Degree of Freedom Systems, Equations of Motions. This is from the course Structural Dynamics by Dr. P. Banerjee. He is from Department of Civil Engineering of IIT Bombay. I hope this solution will help you clear your doubt. Thank you.